Let us continue our discussion of robust LP. In the example seen earlier, we had a constraint of the form A transpose X less than equal to B, and we were interested in satisfying it for the case when A belongs to an ellipsoid. It is actually possible to derive the same robust LP starting from completely different assumptions. Let us take a look at the notion of stochastic uncertainty or stochastic robustness. So instead of saying that A belongs to a certain ellipsoid, let's say that someone says that I want to satisfy A transpose X less than equal to B, but I know that A is actually random and it is normally distributed with mean A0 and variance P. So the vector A is a multivariate normal with mean A0 or covariance matrix P. Then if we assume this, what is the distribution of A transpose X? You can observe there that A transpose X is also normally distributed with what is the mean of A transpose X? So expected value of A transpose X is given by A naught transpose X. So the mean is A naught transpose X, and the covariance of A transpose X is given by the expected value of norm of A minus A naught transpose X square, right? So this is given by X transpose Px. So the covariance matrix or the variance of A transpose X, which is a scalar, is given by X transpose Px. So if someone says that I want to satisfy A transpose X less than equal to B, where A is this random variable, I could ask with what probability you want to satisfy, because A is random. So obviously A transpose X can be anything from minus infinity to plus infinity. So it cannot generally be satisfied. So therein comes the notion of stochastic robustness. What we are saying that instead of this constraint, we will replace it with probability of A transpose X less than equal to B greater than equal to some limit. Let's say epsilon. For example, epsilon could be 0.99. So in other words, we want to say that the constraint is satisfied with high probability. So this is called with high probability. I want to satisfy the constraint. Now, what is this value? If you know about normal distribution, you can see what is the tail probability of a normal distribution. I can write it as phi. So phi is the normal CDF, right? Phi of B minus A naught transpose X subject to square root of X transpose Px. Remember that phi is the CDF of normal distribution. So you can think of it as square root of 1 by 2 pi minus infinity to x e raised to power minus t square by 2 dt. So this is the CDF of normal random variable, which is zero mean and unit variance. So if I substitute this, what does it imply? I can write it as B minus A naught transpose X divided by square root of X transpose Px greater than equal to phi inverse epsilon. Whatever that epsilon is, phi, I can always take an inverse of phi because phi is a CDF, and in fact for Gaussian it is a strictly increasing function. So this constraint can be written as A naught transpose X plus phi inverse epsilon times norm of square root P X norm less than equal to B. So this constraint can be written in this form. Now if you compare this constraint with what we obtained for the case of ellipsoidal uncertainty, so let me just write that constraint also here. The constraint we obtained for ellipsoidal uncertainty was square root P times X norm less than equal to B. So the only difference between these two constraints is that I have a scaling factor, and this scaling factor is actually positive. So phi inverse of epsilon is positive whenever epsilon is greater than 0.5. So as long as epsilon is greater than 0.5, this is actually a SOCP. So in other words, the ellipsoidal uncertainty region that we specified for A can also be interpreted as the high probability region, that is where A should belong, so that this constraint is satisfied. Right? So there is a one-to-one equivalence between the two. Except that we can control, in this case we can control it slightly better because we have this phi inverse epsilon with us. So instead of 0.99 I can also have 0.9, and then we are satisfying the constraint with slightly lesser probability, and therefore the effect of that is that this scale factor multiplies with p. So therefore we have a larger region. So more uncertainty in A, or in other words, the problem is more robust. So these are two applications where SOCP arises. If A is random, or if there is an ellipsoidal region where A belongs, then we can specify the robust version of a linear program as an SOCP.